This is a Galileo thermometer. It's a sealed glass tube with a series of smaller glass bulbs which are filled with a colored liquid. The bulbs inside are suspended in a clear liquid, and each bulb has a unique tag labeled with a specific temperature, and you use those tags to gauge the temperature of the room. And the idea is that whichever bulb is floating in the middle, like for instance the orange one here, is the one with the accurate temperature reading.
Alright, so first I want to take a brief recap of the Archimedes principle that we are going to use in our dissection. So for an object submerged in a fluid, the hydrostatic pressure will act on it from outside and normal to its surface. And we can get the buoyancy force by taking the surface integral of all those pressure, or we can use a simple metric, which is taking the same control volume but with static fluid. And like I did on the right side right here, and we can get the buoyancy force to be equal to the weight of the displaced fluid. Using the Archimedes principle, the net force on the object can be composed of the weight downward and the buoyancy force upward. From the equation of total force, we can see that the average density of the object versus the density of the fluid will determine the direction of the net force. If the average density of the object is larger than that of the fluid, the force will head downward and the object will sink. It will float if the density is the same, and it will float up if the density of the fluid is larger. When the temperature of the thermometer changes, the object's volume will stay around the same, and so does its density. However, for the fluid, it will have much higher thermal expansion coefficient, and thus a very high change in volume, as shown in the first equation. Also, the fluid inside the thermometer is of constant mass, so the density will be inversely proportional to the change in volume. If the temperature increases, the volume will increase and the density will get lower. If the temperature decreases, the density will rise instead.
The liquid inside of a Galileo thermometer is not mercury like a common thermometer today. The liquid inside of a Galileo thermometer has to be a liquid with a very high thermal expansion coefficient, so its density can change easily with temperature changes. The liquid should also have a high Reynolds number and a low viscosity. That way the bubbles can move very easily through the static fluid. And it should be a translucent liquid. That way you can actually see the bubbles and read them from the outside.
The cylinder's diameter should allow the bulbs to stack up so we can see the order and measure the temperature easily. Too large of a diameter can cause the order of the bulbs to change, which makes it harder to read the temperature quickly. In the case of a high change in temperature, the fluid's expansion will be considerably large, so to accommodate for that situation, we allow some headroom at the top for the increased volume. If we don't do so, stress on the cylinder might cause the thermometer to crack and spill out the fluid inside. Inside each bulb, a different fluid with coloring added is used to calibrate the mass of the bulb such that their density without the metal tag is near that of the surrounding fluid. Now we change the bulb's average density to the density of surrounding fluid at a certain temperature by changing the weight of the metal tag, since we can fine-tune that more precisely than the mass of the water inside each bulb.
Now we will see a Galileo thermometer in action. Here we see a Galileo thermometer with bulbs adjusted to the liquid density at a 5-degree difference between the ranges of 60 to 90 degrees Fahrenheit. We will see what happens when the liquid inside of the Galileo thermometer is heated to 75 degrees Fahrenheit. As was stated earlier, as the liquid inside of the Galileo thermometer heats up, its density will lower. This means that the bulbs that are calibrated to a higher density, i.e. the bulbs at a lower temperature, will sink first, meaning that the bulb left floating in the liquid corresponds to the temperature. The 60, 65, and 70 degree Fahrenheit bulbs have all sunk to the bottom, while the 75 degree bulb lies at the exact same density as the surrounding liquid, letting anyone observing that the outside temperature is a nice 75 degrees Fahrenheit. Now we will see what happens when the Galileo thermometer is exposed to a temperature that does not have a corresponding temperature tag. Like before, as the liquid around the bulbs heats up, its density is going to lower. So the higher density bulbs, the ones that are marked at a lower temperature, will sink first. The 60, the 65, 70, etc. Till finally the 85 degree bulb falls as well. However, the 90 degree bulb stays, meaning that the temperature lies somewhere between the two.
And these are the sources that we used in the making of this project. Thanks for watching.